The Gaussian elimination is a method that is normally used to eliminate variables in subsequent equations, especially in linear equations, so that we get what is known as a system that is in row echelon form. And then thereafter, the last equation usually simplifies to getting the value for the last variable, and then we back substitute to get y, and then substitute again in the first equation to get x. And that is known as back substitution. Once you've got z, you go back and substitute in the second equation, and then you take x and y and z, go and substitute in the first equation. Now let's do it using the systems. How then do we do the elimination of variables? Note that these are the three equations that have been given to us. In order for us to remove negative x in the second equation, we can simply add equation 1 and equation 2. And then our answer replaces the second equation. That's exactly what you did here. Equation 1 plus equation 2. Note that we are just adding them because it was x and minus x, so that we eliminate x in the second equation. Note that you are adding the equations, so it gave us also the coefficient for y and the coefficient of z and also the constant. And note that it replaces the second equation. So what you do now, you have to write down the new system. The first equation that has not changed, the third equation that did not change, and the second equation that has changed. Now the next thing, remember, we have to eliminate x in the third equation as well. So we use the first equation to eliminate that x in the third equation. So we multiply the first equation by -2. Remember, you cannot just multiply -2 to x only. You have to multiply to the whole equation. So -2 times the whole equation. You add your answers to the third equation, and what you get replaces the third equation. It does not change the first equation, but changes the third equation. So you'll have -2 multiplied by x plus 2x to eliminate x in the third equation. Once again, you'll have -2 times -2y plus -5y. And then -2 times 3, which is -6, plus 5z. -2 times 9 plus 17. And what you get will replace the third equation. That's what we did. We're adding -2 times equation 1 to equation 3. And the results will form the new equation 3. And note, you always write down the whole new system. Equation 1 does not change. Equation 2 does not change. The whole manipulation changes equation 3. And those are the results for equation 3. The next step is to eliminate negative y from the third equation. Remember, what we want is a triangular form where the first equation has got x, the second equation does not have x, and the third equation does not have x and y. And the only way to eliminate y in the third equation is to add equation 2 and equation 3. And then you replace your answer as equation 3. So you will have y minus y, that's a 0. So that eliminates y, and then you have 3z minus z, that gives you 2z. 5 minus 1, that gives you 4. And then you write down the whole system. That's exactly what we got. Note the first equation still remains the same, second equation the same, then we have 2z is equal to 4. And then thereafter we work it out, and here we realize that we can be able to solve for z. You can, even at this stage, divide the third equation by 2 and replace equation 3, and then thereafter do the back substitution, where you take the value of z, substitute into the second equation, take the second equation, the value for y and z, substitute into the first equation. That's exactly what we did. So we multiplied equation 3 by half, and we replaced equation 3, and then we wrote down the new system, and then thereafter did what we call the back substitution to solve the equation. Now we can use a matrix format. We can use a matrix format to solve the systems of equations using exactly the same thing that we've done. But now, instead of having x, y, and z as variables, what we do is to formulate an augmented matrix before we perform the row operations. So we formulate an augmented matrix which has got A, which is the matrix of coefficients of the variables, and C, the matrix of constants. So all the coefficients of the variables go into as matrix A, and C are all the constants in their order. So the matrix form we know is in that order. So now we have to formulate the augmented matrix and then thereafter perform the same row operations that we did for the equations. Note that we took the same system as we had just done. Here is the matrix format that we had already formed. Then we augment the two matrices. We augment matrix A and matrix C, and then perform row operations. In order to eliminate -1, we add row 1 and row 2. Remember that we had said equation 1 plus equation 2, and it forms the new equation 2. So equation 1 does not change, equation 2 does not change, but now because we're dealing with matrices, it's rows. Row 1 still remains the same, row 3 does not change. We're only changing row 2. So the only reason why we're changing row 2, we want to eliminate -1. But what you do to one entry in a row, you do to the whole row, just like when you were doing it to one variable, you are doing to the whole equation. So we're adding 1 and -1, that gives us a 0. -2 and 3, that gives us a 1. 3 and 0, that's a 3. 9 and -4, that's a 5. Now the next step is to eliminate 2 in the third row, because we're trying to make sure that we have 0 coefficients for variables x and y in the third row, x in the second row, because what we are looking for is that row echelon form. Now in order for us to eliminate that 2, we multiply row 1 by -2, just like what we did. We said equation 1 will be multiplied by -2, and your answer will be added to equation 3, and your answers will replace equation 3. Note the format that we're using there. -2 times row 1 plus row 3. Substitute in row 3. So negative 2 times 1 is negative 2 plus 2, that gives us a 0. Negative 2 times negative 2 is 4. 4 minus 5 is negative 1. Negative 2 times 3 is negative 6. Plus 5, that's negative 1. Negative 2 times 9 is negative 18. Plus 17, that gives us negative 1. The next step that we have now is to eliminate the coefficient of y in the third row. The easiest thing that we see, because we still have 0 and 0 there, we can just add row 2 and row 3, and our answer replaces row 3. So we write here R2 plus R3 and substitute in R3. We add 0 plus 0 is 0. 1 minus 1 is a 0. 3 minus 2 minus 1, that gives us a 2. 5 minus 1, that gives us a 4. You can even leave it here because it's already in row echelon form, or perform the last part, which is half times row 3, substitute in row 3, so that you have 1, all ones on the main diagonal, so that we have 1 and 2. Otherwise, this last step is not necessary. You can stop here, and then you'll have 2z is equal to 4, which allows you to solve for z and get z equal to 2. You do the back substitution like we did before. Note that once we get the row echelon form, that is 0, 0 for the x variables in the second and the third row, and 0 for the y variable in the third row, then you can formulate the three equations based on what you have. Note that 1 is a coefficient of x, minus 2 is a coefficient of y, 3 is a coefficient of z, equal to 9. For the second row, the coefficient of x is 0, so you have y plus 3z equal to 5. The last one is z equal to 2. Then we continue with the back substitution. Z equal to 2, substitute into the second equation, get negative 1, and then we go back and substitute into the first equation to get x equal to 1. Now, here in this example, we'd like to figure out the row operations that were performed to change the first augmented matrix to the second augmented matrix. I'm hoping that you're noticing here that the only thing that happened here was to exchange row 2 and row 1. So you can write it. I'm hoping that I'll be able to, my mouse will be able to do it properly. It's row R1 with a double arrow, row 2. R1 double arrow R2, to show that all you did was to exchange the two rows. That's it. Nothing else happened. And you can do this because remember, 0 has to be in the second row, not in the first. So you can just do the interchanging of rows. Then B, what happened between the first augmentation and the second, producing the second? All we know is that the only change was done in the first row. So it's half R1, substitute in R1. Here in C, what we're noticing is that from the first augmentation to the second, the change is in the third row. So what could have happened is that we multiplied negative 2 to row 1 and we added that to row 3, substituted in row 3. You can check that and see whether those are the correct row operations. Now we're asked to use the Gauss-Jordan elimination. The Gauss-Jordan elimination takes the Gaussian elimination further. For the Gaussian elimination, we know that in place of 3, what we need is a 0. In place of 2 in the third row and 4 in the third row, we need zeros. But for the Gauss-Jordan, it wants you to change the whole matrix of A into an identity matrix. So you perform row operations that will change the whole matrix all the way until you get the last row operation giving you an identity matrix on the left, and then your solutions will be on the augmented side. Please go through the steps and see whether you understand the row operations that have been performed, and note that straight from the last augmented matrix we get the solution: x equal to 2, y equal to -1, and z equal to -2 without back substitution. Please go through these steps and see whether you agree with what has happened here and whether you would get the same solution. And then again, use the Gauss-Jordan elimination to do number B and C. Now we go on to the determinant. Note that we can only find the determinant to a square matrix. That is a matrix with equal number of rows and columns. One of the methods that can be used is using the minors and cofactors. So how do you find a minor? If you've got a matrix, then you are looking for a minor Mij, which corresponds to an element, a particular element Aij. You delete the ith row and the jth column, and then find the determinant of the remaining elements. So that means if it's M11 that you're looking for, you delete the first row, first column, and then find the determinant of the remaining elements. Then the cofactor Cij corresponding to that minor Mij is given by the formula -1 to the power I plus j times Mij. Therefore, the determinant is then given by the entries of that row multiplied by their column, and you sum them up. So if you decide to use a particular row, then it will be that row multiplied by the corresponding cofactors, and you add your answers up. If you choose to use a column, we can still use the column. A row and a column for that particular matrix must give you the same answer. So let's do a particular example so that we see this. Also, there is another method that we use, in particular for a 3 by 3 matrix, where what we do is to repeat the first column, we repeat it, and the second column, and then we formulate diagonals, the ones going down we add their products, the ones going up, we subtract their products. So all you need to do is to take the first column, repeat it, second column you repeat it, and then make sure that the diagonal goes through 3 entries. Each diagonal must go through 3 entries. So as you notice that you'll only be left with A22 at the end that is not touched by the diagonals, and A21 on the other side not touched. Note that the ones going down are added and the ones going up are subtracted. Note you multiply. So it should be A11 times A22 times A33 plus A12 times A23 times A31 plus A13 times A21 times A32 minus, remember we subtract those ones, A31 times A22 times A13 minus A32 times A23 times A11 minus A33 times A21 times A12. That's another method of finding the determinant. But now for an example, let's just quickly find the minors and cofactors of this particular matrix. As we had said, for M11, what we do, subtract the first row and the first column, and then find the determinant of the 4 remaining elements. It will be minus 1 times 1 minus 0 times 2, and we know the answer should give us that negative 1. So it means if we are looking for M22, that means we delete the second row and the second column. We'll be left with 0, 4, 1, and 1. So it will be 0 times 1 minus 4 times 1, and the answer would be negative 4. Please check this minus and see if you're going to get the same answers. Remember, for the cofactors, we use the formula. We need, if it's C11, it will be M11 multiplied by negative 1 to the power 1 plus 1. So M12 will be multiplied by negative 1 to the power 1 plus 2 to get the cofactor C12. And then in order for us to get the determinant, when we use the first row, we go back to the original matrix, A11, C11. So it's the entry multiplied by the corresponding cofactor plus all the entries in the first row multiplied by their corresponding cofactors, and you sum them up, they give you an answer which is 14 for this particular matrix. Note that if we had chosen to use the second row, again we're getting 14. Even if you'd chosen to use the third column, the answer will still be the same. You can test it out. If you use the second column, see whether you are going to get the same answer. Now, as an exercise, find the determinant of matrices A, B, and C using both methods. That means using minors and cofactors, as well as the one where you duplicate the columns. So you duplicate 0, 3, 4 and 2 minus 1, 0. And then you formulate those 3 diagonals going down and those 3 diagonals going up, adding the products that go down and subtracting all the products that are going up. See if you're going to get the same answers. example, in the example that we have here, we have A and B square matrices. Note the order has been given. Both of them are 4 by 4 matrices, and the determinant of A is given to be -5 and the determinant of B equal to 3. A, we're asked to find the determinant of AB. First things first, you need to write down the property that we're using. It means that it's the determinant of A times the determinant of B, and then substitute. So I believe we'll get -15. And then for B, the determinant of A cubed, we also use the same property. So it's the same determinant of A times the determinant of A times the determinant of A. And then we have -5 to the power 3. That gives us -125, I think. Then for C, the determinant of 2B, it will be equal to 2 to the power 4 multiplied by the determinant of B, and you get the answer. Now the determinant of D brings in the property of the transpose. So we have here the determinant of AB transpose. It means that first things first, you start within that determinant, removing the bracket. We have the determinant of B transpose A transpose, then which is equal to the determinant of B transpose times the determinant of A transpose. And then we know the determinant of a matrix is equal to the determinant of its transpose. Then we substitute. Then E is, we know that the determinant of an inverse matrix is 1 over the determinant of the original matrix.